This is lecture 9 for Chem 223. Today we will be talking about titrations and the math that loved them. So this lecture is going to come along with another handout. So let me pull that up really quickly for you. On this handout, the first page has problems that I will be going over during the lecture, and then also the other notes down here will be going along with the lecture. And then, of course, there will be a few extra practice problems for you to work through on your own with a key down here for figuring all this stuff out. All right, so what we're going to do, though, today is look at a titration curve. We're going to figure out the features of a titration curve, the different points on it, and we're going to talk about how to calculate the pH at different points on this curve. So the first point we're going to talk about is right here where the slope of our curve is the steepest. Let me back up a little bit. On the x-axis down here we have the volume of our titrant, and on the y-axis we have the pH of our solution. And with that, let me ask you, is this the titration of a weak acid with a strong base, or is this the titration of a weak base with a strong acid? So think about that for a minute, and you can pause the video if you need to. But the answer is that this is the titration of a weak acid with a strong base. How do we know that? Well, because we're starting at a low pH and going to a higher pH, right? Acids have a low pH, and so if this is starting at a low pH, we're titrating a weak acid with a strong base. Right, and at the point where all of our weak acid is used up, or the equivalence point, where we have a stoichiometric ratio between our acid and base, is the point where the pH can change the most rapidly. So once you're out of acid that is preventing the base from dramatically increasing the pH, once all that acid's used up, the pH goes up really quickly, and your equivalence point is found on this titration curve as the steepest point in the curve. Okay, the next point we're going to talk about is the half equivalence point. So this is the flattest point on this curve before the equivalence point. Of course, after the equivalence point, this starts getting pretty flat. But before the equivalence point, the half equivalence point is where half of your analyte has been used up. And of course, around this is our buffering region. So in this region, our acid is, of course, getting turned into a base. And we have a good buffer region, or a region where our buffer is strongly resistant to pH change when the ratio of acid to base is within a factor of 10 of one another. All right. And the last point, or the last region we'll cover on this titration curve, is the area beyond the equivalence point. So in this region, we just have leftover strong base that hasn't been used up in the titration. And in this region, our pH of our solution is approaching the pH of our titrant. All right, so now what we're going to do is talk about the math for these different regions and how we calculate the pH at these different spots. And so we're going to start with the starting point. All right, and so for all these calculations, we're going to consider a 100 ml solution of 0.1 molar acetic acid. I've got the Ka value for acetic acid listed up here. And we're going to be titrating this acetic acid with a 1 molar strong base solution. And so we can just pretend that this is NaOH or any other strong base that we want. Of course, it can't be calcium OH2 because that would be too many OHs for us. So we're going to just consider this to be NaOH. And what we're going to do on this first slide is just calculate the initial pH of this solution. So now, of course, we've switched to a completely word and numerical representation of that calibration curve. At the end, we will go back and talk about the calibration curves. So if you're a visual learner, we will get back to that. But how do we calculate the initial pH of this solution? Well, this is what you've already been doing with the previous lectures and homework assignments. But here we're going to just set up the reaction here that's going to happen when we put acetic acid in our water. Of course, the water is going to steal a proton from that, so we're going to get that H plus and the conjugate base over here. Then we're going to set up our ice table. Our initial concentration for our HA is just going to be the 0.1 molar that's given up there. Our initial concentration of the H plus and the A minus, of course, are going to be 0. There is going to be some small amount of H plus from the autoionization of water, but we're going to assume that's small enough that it's not going to matter here. And of course, that's going to be true given this high concentration of acetic acid. Now, if your next question is, well, how do we know which concentration here means that we can assume that the H plus concentration is low? And for that, I will refer you back to that pH handout that we did on lecture 8, I believe, where I had you calculate the pH for a bunch of strong bases and figured out the concentration range where you actually have to consider this, okay? So that's going to be on you a little bit to learn. And of course, there's not going to be any acetate ion in our solution to start with. These are all going to change by X. The acid's concentration is going to decrease by a value of X. The proton and A minus concentrations are of course going to increase by plus X. And so on the equilibrium line here, we get these following values. We plug these in for Ka, or into our Ka equation. We solve for X using the quadratic equation, take the negative log of that to get our pH. I am, of course, rushing through this. I recognize that. I won't rush through the rest of the math so much, but this math we've already done a few times. I will make this point here. If you forget the form of the Ka equation, that is okay. If you just remember that all K equations are exactly the same. They're always just products over reactants. If you forget the specific form of the Ka equation, you can just remember that. The same is true for the Kb equation and the Kw equation and all K equations, assuming they're a capital K. Lowercase k's are, of course, a different story. But this is, of course, how you're going to calculate the initial pH of your solution. Now, though, let's titrate it a little bit, and let's add 5 mils of our base. So remember that this is a 1 molar strong base solution, and we're starting with 100 mils of 0.1 molar acetic acid. What we're going to do here is actually assume that the acid reacts first with the base, and then second it'll interact with the water and it'll undergo equilibration, where it tries to get its concentration of acid and conjugate base at a ratio that gives it a Ka value of 1.8, etc. All right. So the first thing we're going to do, like I just said, we're going to react our acid with our strong base. When that happens, our OH minus, of course, is going to strip off a proton from our HA. We're going to get water and A minus left over. And a strong base will react completely with a weak acid. That is another key component of strong bases that you need to remember. Strong bases react completely with weak acids. Likewise, weak acids react completely. Oh, I'm saying the same thing. Likewise, a strong acid will react completely with a weak base. All right, now instead of doing an ice table, though, we're going to switch to what's called a BCA table. Fundamentally, a BCA table is very similar to an ice table. The big difference here is that with a BCA table, we're actually dealing with moles. In an ice table, we're always dealing with concentration. Usually we're doing that in molarity, but it is always in concentration. And a BCA table is in moles. The acronym for BCA is very similar to ICE. So for ICE, it's initial change in equilibrium. For BCA, it's just before change and after. This table is going to work functionally the same as an ICE table, but we give it a different name so that we can remember that we're doing this in a different unit basis. where here we're doing moles, not molarity. And why we're doing that will become obvious as we work the problem. But so what we need to do is figure out how many moles of HA and OH minus are present, and of course water and A minus. So we know the answer to the A minus already. We know there's 0 moles present of that. For water, we just know it's present because it's a bulk solvent, so we don't really care the exact number of moles. For HA, we're just going to take this initial concentration of 0.1 molar, multiply it by the 100 mils, but of course that would give us the wrong units, so we need to convert the mils to liters. So this would be 0.1 molar times 0.1 liter. That will give us 0.01 moles of HA. We're going to do the same for the OH minus here. We're going to take the 1 molar concentration and multiply that by 0.005 liters to get 0.005 moles. Now, what are we going to write here for the change? Well, we just said that the strong base is going to react completely with the weak acid, and so all of this strong base is going to be used up. So it is going to be changed by negative 0.005 moles. And of course, the ratio between the weak acid here and the strong base is a 1-to-1 ratio. And so that's going to change by the same amount. It's going to change by negative 0.005 moles. And our conjugate base is going to gain 0.005 moles because, of course, for every mole of HA that's consumed, we produce 1 mole of A minus. And then after, we just add lines 1 and 2 to get our after values for the number of moles of HA and A minus. We need to calculate our pH. So how are we going to do this? Are we going to use an ice table? We could, but usually in this range you start running into some weird math that wasn't accounted for when the ice table method was originally conceived. So for this whole range, it's generally okay just to use the Henderson-Hasselbalch equation. So here, of course, the pH is going to be equal to the pKa of our acid plus the log base 10 of the concentration of the conjugate base divided by the concentration of the acid. So let's plug in some numbers here. You'll notice also that here we don't actually have the concentrations of A minus and HA, we just have the number of moles, but we have the same number of moles in the same solution, so we would divide these number of moles by the same volume, and we're going to have volume divided by volume here, so those will cancel out. So we can actually just use the number of moles in the Henderson-Hasselbalch equation as well. We don't actually have to worry about calculating the actual concentration just yet. So here our pH is going to be equal to our pKa, which is going to be the negative log base 10 of our Ka value that's given up here, which is 1.8 times 10 to the minus 5th. And then we're going to add that to the log base 10 of 0.005 moles divided by 0.005 moles. When we plug all that into our calculator, or if you are doing what I would like you to do and plugging this all into Excel, then you will come up with a number of 4.74. Of course, you should get 4.74 whether you're doing this in Excel or calculator. But that is our answer. All right, now let's add a little more base to this solution. Now let's calculate the pH at 10 mils of base being added. So here again, we're going to have to write out our reaction that's happening between our acid and our base. I'm sorry, I went back a little bit. And that's, of course, going to give us water and conjugate base. We're going to write out our BCA table again. We're going to calculate the number of moles of each of these guys. But here you'll see we're starting with the same number of moles of HA. So we're assuming this is a brand new calculation. You don't have to remember anything you did in the previous calculation. That's a question that a lot of students happen. Are these successive calculations? Absolutely not. Pretend like this is the first thing that's happened, right? So we're starting with 0.00, So we're starting here with 0.01 moles of HA, reacting with 0.01 moles of OH minus. And that means that when we react these, all of the HA is going to be consumed. And of course, we're starting with 0 moles of A minus and producing 0.01 moles of A minus. All right, so now we've used up all of our acid, all of our base, and we've converted it all into conjugate base, right? So now that it's all conjugate base, how are we going to calculate our pH? Well, here again, we're actually going to use an ice table now. We can't use the Henderson-Hasselbalch because we have no acid. But what we have to do is notice we don't have the concentration of the A minus, so we actually have to calculate the concentration of the A minus. So we're going to take the number of moles there, and we're going to divide by the total volume. And this is a spot where a lot of students mess up, make silly errors. This is a spot you will probably forget once or twice while you're doing these calculations. But the total volume is your starting volume. So we started with 100 mils, and then we added 10 mils of base to this. So our total volume now is 110 mils. So we'll divide 0.01 moles by 0.11 liters and get a concentration of 0.0909 molar. All right, now we can set up our ice table and calculate our pH, except for one last thing. Notice that we still have the Ka up here. If we try and do our ice table with our Ka value, again, we're going to run into some weird math, and we're going to probably get some sort of negative value for our concentration. So what we actually need to do is calculate our Kb for this conjugate base. So if you'll remember, the Kb is equal to Kw divided by the Ka, and we're going to just use 1 times 10 to the negative 14th for Kw here. Then our Ka, of course, is just this value from the question. And so our Kb is going to be 5.6 times 10 to the negative 10. Now we are actually ready to set up our ice table. We're going to start by setting up the reaction that is occurring here. So now we're just considering the reaction with our conjugate base and water. And so that's going to form OH minus and H plus. Now here you might look at this OH minus and think, wait, if OH minus was a strong base previously, why is it not a strong base now? Well, that's a very philosophical question. But the real reason is because when we're doing the math here, the OH minuses here are identical chemically, but when we're modeling this whole thing and running the math through to calculate our pH, we just need to consider them as separate species. And so this OH minus we're not going to consider as strong as the OH minus previously. If you have questions about that, feel free to let me know. All right, but now we can set up our ice table. Our starting concentration of A minus here is 0.0909 molar. We're going to start with concentrations of OH minus and HA of 0 and 0. Of course, those were present initially when we put them in, but again, we're considering the reaction between the acid and base first, and then pretending that the reactions with water happen second. Okay? So now, then we just have to change the values of these guys. The A minus is going to change by negative X molar, and I'm leaving the molar in here just to emphasize that the ice table is in concentration, not in terms of moles, whereas the BCA table is in terms of moles. And we get our change here, right? And then we set this all equal to Kb. We plug these X values in for the products on top, and the reactant values go on the bottom. That's equal to our Kb value of 5.6 times 10 to the negative 10th. We solve that for 0 and then use the quadratic equation to solve for X, and we get a value of X of 7.11 times 10 to the negative 6th. And then, of course, we need to take the negative log of that to give us a value of 5.15. Now, you might make a big mistake here and think that we are done, but this X value is not the concentration of protons, right? We just calculated the concentration of the OH minus. So when we take the negative log of that, we're actually calculating the POH. So the POH is equal to 5.15. So now how do we get the pH out of that? Well, our pH plus our pOH, if you remember, is equal to 14. And if you don't remember, then the pH plus the pOH equals 14, and now you know. So then we just solve this for pH, so our pH equals 14 minus our pOH, so our pH is equal to 8.85. All right, now let's come back to our equilibrium curve and put this all into context and summarize what we've just said. So here is our calibration curve. Again, this is a weak acid being titrated with a strong base. So we're starting at a low pH, going to a high pH. And at the different points on here, if you're calculating the initial pH of this titration, then of course you're just going to use an ice table, and you're only going to consider the acid because you haven't added any base. For this buffer region, or the region between the starting point and the equivalence point, what you're going to have to do here is do a BCA table where you calculate how much acid is left, how much was used up and converted into A minus, and then from there you can use the Henderson-Hasselbalch equation to calculate your pH. At the equivalence point, where you just have conjugate base left over, then you're going to do your BCA table to convert all of your HA to your A minus, and then you're going to use the ice table from there. You're going to have to calculate your KB value and consider all of this as being a base reacting with water to get some conjugate acid, etc. Now, I will point out at this point that some of you will be able to do BCA tables in your head, and if you're able to do that, that's just fine. If you're out there now thinking, how could somebody do a BCA table in their head? Don't worry about it, and just try and write it out all on paper. Even if you can do it in your head, more than likely you're going to make less mistakes if you just write it out anyways. But if you can do it in your head, that's fine. All right, but what about this other region, this big shadowy place where the hyenas live? How do we calculate the pH over there? Well, over here we have excess OH minus, so we have excess strong base left over, and we also have some conjugate base in there. How do we add those together to figure out our pH? Well, we actually are going to not add them together. We're going to assume that all of the pH is resulting from the OH minus and that the A minus has a negative effect on the pH. And that's generally a pretty good assumption, except for maybe the steepest part of this curve right after the equivalence point. And so for most cases, just considering the OH minus is fine. So what we're going to have to do there is a BCA table to figure out how much OH minus is left, and then do a strong base calculation, right? So what we're going to do, calculate how many moles of OH minus are left over. Then you have to determine the concentration of the OH minus, right? So that's moles of OH minus left over divided by the total volume. So that's your starting volume of analyte plus your volume of titrant that you added. And then you'll take the negative log of that. That'll give you your pOH. And then from there, you can calculate your pH. All right, now let's look at the same thing for a weak base being titrated with a strong acid. So this is the same thing generally, except now you have your titration curve flipped over. We're starting at a high pH and going to a low pH, but the points on this curve are still the same, and we calculate the pH roughly the same. So at the starting point, you're going to have a weak base. You'll do an ice table and use your KB value to calculate your pOH, and then convert that to your pH. For this buffer region, where you'll have some A minus and some HA, you'll have to do a BCA table to determine how much A minus and HA are in there. And then you will have to use the Henderson-Hasselbalch equation. For the Henderson-Hasselbalch equation, you'll still have to calculate the pKa of your acid. So if you're given the Kb of your base, you'll convert that to the Ka, and then take the negative log of that to get your pKa. At the equivalence point, all you have left is conjugate acid. So you'll have to do a BCA table there and then convert the number of moles of acid to the concentration of acid by taking the number of moles of acid, dividing by your total volume again. Then you'll do an ice table. You'll use your Ka value now because you're dealing with an acid, and solve that out for your pH. And then beyond your equivalence point here, you'll have your HA that's been generated from your base, and you'll have excess protons from your strong acid. And in this region, we're going to do the same thing as with the weak acid, strong base titration. We're going to pretend like the HA isn't really contributing to the pH very much, and we're going to assume that the pH is all resulting from our excess acid, right? And then just figure out the pH resulting from that. Lastly, let's ask the question, what happens though if you try and titrate a strong acid with a strong base, or vice versa? Or in general, what happens when you mix a strong acid with a strong base? Well, there's only 3 possible outcomes here. Those outcomes are, number 1, all of the acid is used up, so we have a little bit of strong base left over. The second outcome is all of the base is used up, we just have strong acid left over. And the third, which is actually really hard to actually get, is all of the acid and all of the base are used up and have neutralized each other. If this is the case, then we're at a pH of 7. Everything's been neutralized. You have a salty solution now. The reason I say that's really hard is to get a pH of exactly 7.00, you have to know the concentrations of your acid and base really well. You have to know the volumes you added. None of that's super important for you since you'll mostly just be doing numerical calculations. But for each of these, you're going to have to do a BCA table to figure out how much acid or base is left over, and then just do a strong acid or base calculation. Should probably not drink any solutions prepared with strong acids or bases, but you should also note that soda has a lot of phosphoric acid in it and has a lot of other strong acids in it, and soda is super acidic. And I don't have any problem with soda from a word of wisdom point of view, but especially since I've been teaching this class, I've realized that soda is really bad for you, especially your teeth. Anyways, that is lecture 9. Let me know if you have any questions or need any help.